Skip to content. MacTutor logo. MacTutor. Home. Biographies. History topics. Map. Curves. Search. Alan Matheson Turing. Quick info. Born June 23, 1912. London, England. Died June 7, 1954. Wilmslow, Cheshire, England. Summary. Alan Turing's work was fundamental in the theoretical foundations of computer science. Thumbnail of Alan Turing. View 7 larger pictures. Biography. Alan Turing was born at Paddington, London. His father, Julius Matheson Turing, was a British member of the Indian Civil Service, and he was often abroad. Alan's mother, Ethel Sarah Stoney, was the daughter of the chief engineer of the Madras Railways, and Alan's parents had met and married in India. When Alan was about 1 year old, his mother rejoined her husband in India, leaving Alan in England with friends of the family. Alan was sent to school, but did not seem to be obtaining any benefit, so he was removed from the school after a few months. Next he was sent to Hazelhurst Preparatory School, where he seemed to be an average to good pupil in most subjects, but was greatly taken up with following his own ideas. He became interested in chess while at this school, and he also joined the debating society. He completed his common entrance examination in 1926 and then went to Sherborne School. Now 1926 was the year of the general strike, and when the strike was in progress, Turing cycled 60 miles to the school from his home. Not too demanding a task for Turing, who later was to become a fine athlete of almost Olympic standard. He found it very difficult to fit into what was expected at this public school, yet his mother had been so determined that he should have a public school education. Many of the most original thinkers have found conventional schooling an almost incomprehensible process, and this seems to have been the case for Turing. His genius drove him in his own directions rather than those required by his teachers. He was criticized for his handwriting, struggled at English, and even in mathematics he was too interested with his own ideas to produce solutions to problems using the methods taught by his teachers. Despite producing unconventional answers, Turing did win almost every possible mathematics prize while at Sherborne. In chemistry, a subject which had interested him from a very early age, he carried out experiments following his own agenda which did not please his teacher. Turing's headmaster wrote, see for example, 6. If he is to stay at public school, he must aim at becoming educated. If he is to be solely a scientific specialist, he is wasting his time at a public school. This says far more about the school system that Turing was being subjected to than it does about Turing himself. However, Turing learnt deep mathematics while at school, although his teachers were probably not aware of the studies he was making on his own. He read Einstein's papers on relativity, and he also read about quantum mechanics in Eddington's The Nature of the Physical World. An event which was to greatly affect Turing throughout his life took place in 1928. He formed a close friendship with Christopher Morcom, a pupil in the year above him at school, and the two worked together on scientific ideas. Perhaps for the first time, Turing was able to find someone with whom he could share his thoughts and ideas. However, Morcom died in February 1930, and the experience was a shattering one to Turing. He had a premonition of Morcom's death at the very instant that he was taken ill and felt that this was something beyond what science could explain. He wrote later, see for example, 6. It is not difficult to explain these things away, but, I wonder. Despite the difficult school years, Turing entered King's College, Cambridge, in 1931 to study mathematics. This was not achieved without difficulty. Turing sat the scholarship examinations in 1929 and won an exhibition, but not a scholarship. Not satisfied with this performance, he took the examinations again in the following year, this time winning a scholarship. In many ways, Cambridge was a much easier place for unconventional people like Turing than school had been. He was now much more able to explore his own ideas, and he read Russell's Introduction to Mathematical Philosophy in 1933. At about the same time he read von Neumann's 1932 text on quantum mechanics, a subject he returned to a number of times throughout his life. The year 1933 saw the beginnings of Turing's interest in mathematical logic. He read a paper to the Moral Science Club at Cambridge in December of that year, of which the following minute was recorded. See for example, 6 a.m. Turing read a paper on mathematics and logic. He suggested that a purely logistic view of mathematics was inadequate, and that mathematical propositions possessed a variety of interpretations, of which the logistic was merely one. Of course, 1933 was also the year of Hitler's rise in Germany and of an anti-war movement in Britain. Turing joined the anti-war movement, but he did not drift towards Marxism, nor pacifism, as happened to many. Turing graduated in 1934. Then, in the spring of 1935, he attended Max Neumann's advanced course on the foundations of mathematics. This course studied Gödel's incompleteness results and Hilbert's question on decidability. In one sense, decidability was a simple question, namely, given a mathematical proposition, could one find an algorithm which would decide if the proposition was true or false? For many propositions it was easy to find such an algorithm. The real difficulty arose in proving that for certain propositions no such algorithm existed. When given an algorithm to solve a problem, it was clear that it was indeed an algorithm. Yet there was no definition of an algorithm which was rigorous enough to allow one to prove that none existed. Turing began to work on these ideas. Turing was elected a Fellow of King's College, Cambridge, in 1935 for a dissertation on the Gaussian error function, which proved fundamental results on probability theory, namely the central limit theorem. Although the central limit theorem had recently been discovered, Turing was not aware of this and discovered it independently. In 1936, Turing was a Smith's Prizeman. Turing's achievements at Cambridge had been on account of his work in probability theory. However, he had been working on the decidability questions since attending Neumann's course. In 1936, he published on computable numbers, with an application to the Entgedankungsproblem. It is in this paper that Turing introduced an abstract machine, now called a Turing machine, which moved from one state to another using a precise finite set of rules, given by a finite table, and depending on a single symbol it read from a tape. The Turing machine could write a symbol on the tape, or delete a symbol from the tape. Turing wrote, 13. Some of the symbols written down will form the sequences of figures, which is the decimal of the real number, which is being computed. The others are just rough notes, to assist the memory. It will only be these rough notes, which will be liable to erasure. He defined a computable number as real number whose decimal expansion could be produced by a Turing machine, starting with a blank tape. He showed that pi was computable, but since only countably many real numbers are computable, most real numbers are not computable. He then described a number which is not computable and remarks that this seems to be a paradox since he appears to have described in finite terms, a number which cannot be described in finite terms. However, Turing understood the source of the apparent paradox. It is impossible to decide, using another Turing machine, whether a Turing machine with a given table of instructions will output an infinite sequence of numbers. Although this paper contains ideas which have proved of fundamental importance to mathematics and to computer science ever since it appeared, publishing it in the Proceedings of the London Mathematical Society did not prove easy. The reason was that Alonzo Church published an unsolvable problem in elementary number theory in the American Journal of Mathematics in 1936, which also proves that there is no decision procedure for arithmetic. Turing's approach is very different from that of Church, but Neumann had to argue the case for publication of Turing's paper before the London Mathematical Society would publish it. Turing's revised paper contains a reference to Church's results, and the paper, first completed in April 1936, was revised in this way in August 1936, and it appeared in print in 1937. A good feature of the resulting discussions with Church was that Turing became a graduate student at Princeton University in 1936. At Princeton, Turing undertook research under Church's supervision, and he returned to England in 1938, having been back in England for the summer vacation in 1937 when he first met Wittgenstein. The major publication which came out of his work at Princeton was Systems of Logic Based on Ordinals, which was published in 1939. Neumann writes in 13. This paper is full of interesting suggestions and ideas. It throws much light on Turing's views on the place of intuition in mathematical proof. Before this paper appeared,